So welcome everybody. Today is April 24th and we are in calculus. So you can see on the screen here, the students who have showed up today, they have spent some time thinking about this preview activity. And the sort of trajectory for today is we're going to start thinking about optimization. So up until this point, what we've been doing is building up some tools, notably the first and second derivative test for finding local maxes and local mins, and inflection points and critical points. And now we're taking one step further to going to application problems, where we actually are going to take some sort of real life scenario and try to find the optimal values that are presented with that. So what we want to do is we're going to transition today from thinking about local maxes and mins into global maxes and mins, or what the book's called. Sometimes they use the word absolute max and min, right? So it'll involve one extra step where we have to maybe consider endpoints than just our critical points. Okay, so with this activity right here, right? So we have our function f of x, and we want to determine all of the critical numbers for our function. So I'll kick it over to the people that are here. So what did we do to find our critical numbers? Yeah, so you took the derivative of this thing, and then what kind of questions did you ask? Yeah, and then you figure out when is the derivative 0, or where is it undefined. Okay, and so let's go ahead and do that really quickly. All right, so we'll jump over to our Blackboard here. All right, so I want to take the derivative of this, and so what I see in the derivative is this 2 is going to go to 0, and then over here I'm going to have to use quotient rule. Okay, so so I'll do low d high, right? So the denominator is 1 plus x plus 1 squared, right? So this is low. The derivative of my numerator is 0, so low d high minus high. And when I take the derivative of my denominator, I get 2 times x plus 1. And then all that's going to be over 1 plus x plus 1 squared, and all that squared. All right, so we took the derivative, and this is going to be one of those instances where simplifying is going to be to our benefit. So notice that all of this goes to 0, right? So we're multiplying this whole thing by 0. And what we get in our numerator is -6 times x plus 1. And then all of that, I'm just going to leave my denominator the way it is. Right, so I get x plus 1 squared. I just squared there. All right, so is this thing ever undefined? Is it ever undefined? All right, so we do have a denominator. We've got a rational function here. Is this ever undefined? What do y'all think? Could we ever divide by 0, right? Is this thing down here ever equal to 0? So when we're thinking about this, I want you to not have to actually do all the algebra, but just sort of think in behaviors, right? Like what's happening to these functions. So if we look down here, this thing right here, right, 1 plus x plus 1 squared, that is, yeah, it can't be 0, right? Yeah, so if I were to look at this, I have something squared, which is always going to be non-negative, right? It might be, this could be 0, but it will never be negative. So if I add 1 to it, it will always be greater than 0, right? So this denominator here will always be greater than 0. So we're never dividing by 0. And the only time that I could be equal to 0 is if my numerator is equal to 0, which means we have a critical point at x equals -1, right? All right, so our only critical point here is x equals -1, okay? Now, part 2 of our question said, hey, let's go ahead and construct a first derivative sign chart, right? So you have a sign chart that looks something like this. I like to put my f prime out here on the left. We put our critical number on the number line. And so we're going to ask ourselves, hey, where is the derivative positive? Where is it negative? And then that will show us where our function is increasing or decreasing. Okay, so observe the denominator is squared, right? So this is always positive. It's never going to change our sign. And so the sign of this, whether it's positive or negative, just lies with the numerator. Okay, so if I plug in numbers over here that are smaller than -1, I'm going to get negative times a negative, which is a positive number, right? So my function over here is going to be increasing. And then if I plug in numbers that are bigger than -1, what I'm going to get is negative times positive, which is going to be negative, right? So what we should see here is, right, my function from -infinity to -1, it's increasing to this point, and it's decreasing afterwards. So I should see that I have a local max at that point at -1. Right, so the first 2 parts here, we do see that we have this local max, right? So part C, it says, does it have a global maximum? So is there a maximum for this, and how do you know? Right, how do we know that we do achieve a global maximum, or how do we know that we don't? So what do y'all think? Is there a place that on this graph that it's bigger than every other output? Like, what would be a way to figure that out? You could Desmos it, right? Yeah, right. So you could look at this. You could plug it into Desmos, right? So if I graph it, right, we'll look at this and we'll say, yeah, hey, right, we can see that, right? Does it achieve a maximum? Well, it looks like this point right here, it seems that's a pretty reasonable candidate, right, for my global maximum. We saw that it was a local maximum, and then, well, from -infinity all the way until this point, we're increasing, right? So our outputs are going to be smaller everywhere to the left, and then it's decreasing forever afterwards. So it will be, right? So it will always be smaller than this point right here. So this is our global maximum. Okay. Okay, so part D, what happens when x goes to infinity or -infinity? Okay, so when x gets really, really big, one of the things that I want to emphasize here is, like, we could use the graph, right, and we could see that behavior. We don't necessarily need to. Okay, so when x gets really big, let's think about what happens to this term right here. X is a really big number, so this denominator is going to be really, really, really big. Okay, so if I take 3 and I divide by a really, really large number, this number is going to be really small. Right, so when x gets really, really large, I'm going to get 2 plus something really, really, really small. Okay, so as x gets really, really large, this is going to get really close to 2. And same when x becomes negative, right? So if x is a big negative number, still this is going to be 3 divided by something really, really big. So this will be a small number. So it'll be 2 plus something really, really small in either case. So we're going to see that the limits go to 2, right? But this is positive, right? So again, this term is positive. We have a +3, a +1, and something squared is always positive. So this will never be negative, right? So it never goes below 2. And so the question is, does it have a global minimum? So what do you think? Does this thing, if you looked at this function, does it actually have a minimum value? Right? Is there some output that's just smaller than everything else? Yeah, so Luke says no, there's not. Because the numbers, they'll just keep getting closer and closer to 2. They'll never get there. Okay, so they're never going to get to 2. They're always just going to be really close to that. Okay, so my question for you all is, well, what if I wanted it to have a global minimum? Right? So maybe this was unreasonable to me. I said, all right, I can't deal with this situation. We need to make a change so that it actually does have a global minimum. I want to keep the same function, but yeah, make a domain. So what kind of so Luke, give me a domain. Throw out some numbers here that we can restrict to. So we're going to restrict our domain to what? Okay, let's restrict to -8 too. Okay, so the way that you do that in Desmos is you put curly brackets here. So you have -8 is less than or equal to x is less than or equal to 2. Okay, and so if I restrict to this domain, now I can ask the question, hey, do I have a global minimum value? And so it seems like based on the graph, right, I have a small value over here that's 2.3. That's my right endpoint. Looks like everything else is bigger than 2.3. I have a max still of 5. And then if I come down here, right, it looks like we're smaller than 2.3 now. And these numbers keep going down, down, down until we get to, looks like 2.06, right, would be our global minimum, would be at this endpoint. Okay, so it seems like going through this, right, so if I were to cut off my function, I could achieve these minimum values, right? So I still have my global max, and now that I've cut it off, I do have a global minimum over here at this endpoint. Okay. So this is the idea. What we're going to be doing when we talk about real situations, often we don't have unbounded problems, right? Things don't always necessarily go off to infinity. There's going to be some sort of domain in which they're being considered, right? Some sort of price range or some sort of time interval. So most of the time when we're dealing with problems like this, we have a restricted domain that we're going to be working on. Okay. All right. So this sort of warmed us up to get us thinking about what types of problems we're going to see. And so what I want all of you to do to think about here for a moment is this next activity, right? So we have a polynomial function. We're going to find some critical numbers, and then what we're going to start to do is change the domain that we're looking at. Okay, so just like we saw before, we're going to restrict the domain. We're going to see how that might affect our maximum and minimum values. Okay, so here's an example. I mean, there's only 5 of us here. So do we all want to stay here, or are breakout rooms better? Do you want me to break us off into rooms, or is it fine just to stay here? Stay here. All right. So I'll let you all talk a little bit and think about this, and we can, and then I'll chime in as things happen. Okay. So bring up, if you're at home, it would be helpful, right? I would do this one on Desmos, right? So it says use a graphing utility. So try to find the critical values by hand, and then just for some practice, and then play around on Desmos. Okay, so everybody's really quiet. I did some work over here. But any questions so far? What did we find for A? The critical numbers in that interval?
You take the first derivative and then you
What do we
find
all get?
0, right?
I got 2.
Plus or minus the square root of 2.
Square root of 2/3. So Luke threw out square root of 2/3. Luke, is that square root of 2 divided by 3 or square root of 2/3?
Yeah, square root of 2/3.
2/3. Is that what everybody else got? Square root of 2/3?
I got plus or minus the square root of 2.
Square root of 2. Okay. So you did get a square root in there. So Luke, when you took your derivative, you brought the 3 down. Did you cancel with this 1/3 right here?
Oh no, I accidentally put 3.
3, yeah, you had a 3x squared.
Yeah.
Yeah, so the 3 and the 1/3 are going to cancel out. Yeah, so I got the same. I got plus or minus the square root of 2. Okay, so what we can do is it says we want to graph this thing. So 1/3 x cubed minus 2x plus 2. Right, so our function is called g. Just be consistent. So 1/3 x cubed minus 2x plus 2. Okay, so our critical values, we said plus or minus the square root of 2. So these numbers right here, we should see that one of them is the positive square root of 2, one of them is the negative square root of 2. Okay, so if I restrict to the interval that they were requesting here, my graph would look something like this, right? So let's double check, -2 to 3, and so we can see our graph, okay? So where does it have the absolute max? Where does it have the absolute min? So looking at our critical values, it looks like here is the negative square root of 2, right? So if we want to double check those, again, we can do something like this with our graph, right? So I can look at these points, and then I can look at the positive side of it as well. Right, so just confirming that, we do have these values here. So what's the maximum and what's the minimum?
The maximum would be negative square root of 2, and then the minimum would be positive square root of 2.
So the minimum, so you're saying this point right here, this is the positive square root of 2, this is the maximum?
Minimum.
Minimum. And then you're saying that this is the maximum? Okay, so what we see, this is a maximum and this is a minimum. But the question is, are they global? Are they global max and min? Right, so this value here, this is a maximum value. But what kind of maximum is it? And this is a minimum value. And what kind of minimum is it?
Those are the local max and mins.
Yeah, so these are local, right? So they're certainly both local maxes and min. So everything close to this is smaller, and everything close to this is bigger. Is this one a global max?
No.
So Caleb, why not? Where is there a point that's bigger than it?
Like around 3.
Okay, so you're saying like if I look over here,
Yes.
right? So this is 3. So it seems like if I go way over here to 3, my outputs are way up here at 5, where my outputs over here are only 3.8, right? So it looks like I have my global max is actually over here, right? So this would be my global max. right? Whereas this one over here is only a local, right? Only local max. So this is the person that they're the best basketball player in their town, but there's somebody else that is a better basketball player another town over or something, right? Turns out that this one is a minimum, and then if I look at the red line, this is my global min, right? So this is the only point that achieves that absolute minimum value. Nothing else is below this 0.114 on this interval.
So even though like for the actual graph it goes lower, since we're looking at the like this interval, that would be the global min.
Correct. Yep. So it's the global max and global min on this particular interval that we've restricted ourselves to. So when we cut the graph off to that interval, this would be our global max. So we're just saying, hey, we're not considering anything outside of this window, right? So we would only restrict our attention just to this particular window right here. And so that would be our global max. And then
Why wouldn't that be the local max too?
Sorry, say that again, Caleb.
Why wouldn't that point at 3 be the local max too?
Yeah, so this just depends on a definitional thing. So personally, I like to think about the endpoints as being local maxes, but a lot of authors don't consider that because you can't pick anything else on the other side of it. So depending on who the author is, it's just how do they define what a global max is or a local max. So a lot of the time, people are going to say you have a local max if you can pick things on the left and the right that are smaller, right? So anything to the left and anything to the right is smaller, whereas there is nothing to the right of this. So a lot of authors for calculus texts don't want to include that as a local max. Personally, my personal preference opinion is that could be considered a local max, especially with the definition that our textbook author chose, which is anything near it, right? So certainly anything near this point is smaller than it, so it would be considered local.
So if this kind of thing was like on a test, would you count that as if we put that as the local max?
I would, yeah. Yep.
Okay.
So I would count that. So again, with web work, depending on how the problem is interpreted, there's different ways that can come up. But like you saw with the other exam, I'll go through and double check everything that was marked incorrect. Okay. All right. So let's clear this stuff and then let's go back. So now what we're going to do is we're going to change this, right? We're going to change these bounds. Okay. So it said we determined the absolute max and min, and now we're going to switch our interval to -2 to 2 and then -2 to 1. Okay. So instead of considering all the way up to 3, let's only consider all the way up to 2. And now the question becomes, hey, what is our global max and what is our global min? Right? So now with this picture, right? Well, do I still take that endpoint, or right? Do I still look over here? Is this still my global optimal value? Seems like this now, right? So this is my global max. And now down here, right, this point is my global min. Okay, so you can see that this depends on our domain an awful lot, right? So what we have to do is consider, right, not only our critical points now, but we also have to consider our endpoints, because it changes what our domain is, right? So this would be my global min value. And well, if we change this again, right, if we consider the interval -2 to 1, right, it changes yet again, right? So now we can see that this point is still remaining our global min, our global max, but our global min has now shifted over here to our endpoint, which is 1, right? So as I'm changing my domain, depending on what interval I want to restrict to, you can see that the global max or the global mins can all be shifted around. Okay, so if I'm looking for a global max or a global min, where would you suggest that people look for them, right? So if you had to give somebody a hint, hey, you want to find the global max, where are you going to look, right? Where would you tell people to look if you're going to find these global max and min values? Anybody have a suggestion? So we can talk about this graph. Yeah, so you can think about it with this graph with the domain, but what about in general, right? So if I just gave you a new graph and a new interval, sort of what process would you walk through if you were gonna guide somebody else to find the local maxes, the global maxes? Where would you suggest that they look? Okay, so to sort of rewind here, when we had our global maxes and our global mins, yeah, look for the critical numbers, right? So you can look for the critical numbers or the highest and lowest points on the graph if you have all the values, right? So remember, a lot of the time before we spent some time talking about families of functions, so you might not be able to precisely view the graph that you want. You might only be able to view the family. So if you do have the explicit values, yeah, you could just sort of visually pick out what the max and min values are. But I like what you said with critical points, right? So we checked all our critical points, but we also checked our endpoints, right? So at every step of the way, we always had our max and min values were either critical points or they were endpoints, right? So as we're going along and we're doing these tests, if we're going to find a global local max or min, we're going to check our endpoints and then we're going to check our critical points. And so those are our candidates that we're going to consider. Okay. So one of the things that we've sort of illuminated here is this extreme value theorem. So I'm not gonna read it to you, but I'm gonna give you the gist of it here. So if you have a continuous function, right? So it's something that doesn't have breaks or jumps or gaps in it, and you look at it on a closed interval, you're guaranteed to be able to find one of those absolute maxes and absolute minimum values. Okay, so as long as it's continuous and you have a closed interval, so you're including the endpoints, you are guaranteed to be able to find a maximum and you're guaranteed to be able to find a minimum, right? Absolute max, absolute min on the graph. So with our first example we saw today, that wasn't the case, right? So we had those tails that sort of went out on the ends. We couldn't find a minimum, but as soon as we cut it off, then we were able to find that minimum value. So as long as you have a continuous function, so no breaks, jumps, holes on a closed interval, you can definitely find those max and min values. Okay. And so this note right here is important, but the essence of it is when you're looking for absolute maximum and minimum values, the candidates are your critical points and your endpoints. So if you're going to find these, what we're going to do is we are going to check our critical points, and check our endpoints, and then see what happens there. Okay. So I want to spend a little bit of time working through this activity. So as many of you have noticed, right, so often the quickest way to find the max and min values is to graph these. So if you have a function, say like this first one, you could graph it and figure it out. But then if we look at part E over here, okay, so this function h of x, notice that we have a parameter. So when we have functions like this, we have a family of functions with a parameter in it. We can't just simply graph that function, right? So graphing it might give us some hints as to where the points are. But if we want to find a formula for that absolute max or min, we're going to have to do out the calculus by hand, or we're going to have to look at the critical points and then look at the endpoints. Okay, so let's take a minute. Let's think through these, let's say A and B, right? I'll give you some time to think through A and B. And then I do want to spend a little bit of time together on part E here, where we have a parameter, and then we can think about how do we find that max and min. Right, so let's take 3 or 4 minutes. So try to find the critical points and then the absolute max and min values of these two functions, A and B. And then we'll come back together. Okay, so feel free to chat here with each other, you know, throw ideas out if you're stuck or what your answers are. All right, so how are we doing so far? Any questions on these, on this first one? Xe to the minus x. If we take a look at this. All right, so what you should be finding here, right, when you take the derivative is that you get, right, you get a critical point at 1. And then if we check the endpoints, right, so if we plug in sort of our values, if we look at it graphically, we're seeing that, hey, we have, you know, it looks like everything else is smaller than this point right here. And we see that this is our global max, and then our global min would be at 0. So any trouble taking the derivative of this one? Okay. Did we get that? Critical points at 1, or does e to the minus x not have a critical point? Yeah, that's a good question. So I think I understand what you're saying. So let's look at this one on the blackboard. Okay, so you have this function. You're going to take the derivative, right? So you get f prime of x is equal to, as you get your first function times the derivative of e to the negative x is negative e to the negative x, and plus you get your derivative of x is just 1 times e to the minus x, right? So I'm going to use product rule here, and so this is negative x e to the minus x plus e to the minus x, which becomes e to the minus x times negative x plus 1. Okay, so Luke, your question was, does e to the x have a critical point? So my guess is you're asking, is this thing ever equal to 0, and is this term ever equal to 0? So if I'm going to get a 0 here, you can see that when x is equal to 1, we're going to, this term right here, negative x plus 1, this will become 0. Okay, but the question is, does e to the minus x provide you a place where this is going to become 0? Right, and so the answer to that question is no. So any exponential function will never become 0. Okay, so this right here, this function is, the outputs are always positive. Okay, so one way to think about that is to graph it, right? So we could separately graph this function e raised to the minus x. Okay, and you can see that when you plug in negative numbers, you get things that are really, really big. When you plug in positive numbers, you get things that are really small, but they never go negative, right? And so they never become 0. So this graph, it gets really close to 0. It keeps getting closer and closer and closer, but it never actually gets there, right? So as we sort of scroll right, you can see that it sort of gets closer and closer to 0, but never actually gets there. So the only critical point that we're going to have for our function is this one right here at x equals 1. Okay. So with a few minutes left, since we talked about this one, x e to the minus x, let's take a look at this other one too, right, where we have a parameter here. We have a negative ax. So very similar, but we're gonna look at the behavior on the interval 0, 2 over a. Okay. So we have x e to the minus ax, and we want to look at this interval 0, 2 over a, and then I can have a on a slider. So what it's telling us is we want a to be something between something bigger than 0. Okay. So it seems like, right, as this moves, right, so you can see that we do have this maximum here, but it sort of changes, right? So it kind of changes what our max and mins are. Right, so here's our function x e to the minus ax. We're on this interval 0 to 2 over a. So how do we find this, right? So you can see how this point's changing. How do I find that point, right? So a common response is, well, we could guess at it, right? You could guess at what that point is. But again, I think we can do a little bit better. So let's jump back over to the Blackboard again, right? And see if we can do something very similar where we take our derivatives. Okay, so when I take this derivative, I'm going to do something that's pretty much the same as what I did before, except now I'm going to have to use chain rule. I'm going to get this additional a that pops out, right? So I'll get x times negative a e to the minus ax plus, we'd have a 1 times e to the minus ax. So we get negative ax e to the minus ax plus e to the minus ax. Okay? And just like I did before, I can factor this term out, right? This e to the minus ax from both of them, and we're left with so we're left with e to the minus ax times negative ax plus 1. And so what we should find here is that we get a critical value at x equals 1 over a. Okay, so by doing this derivative out by hand, I'm actually able to find a formula, right? So instead of sort of just guessing at what that maximum value might be, I'm able to, compute it directly. And so let's go back to our Desmos graph and see if we can make some sense out of this. So I'm going to have the point 1 over a comma f of 1 over a. All right, I can track this point on my graph for any value of a, right? And so what we see here is, right, it seems that my maximum value is, at this point, 1 over a, comma f of 1 over a, right? So this will always be my maximum. And then looking around, my minimum value appears to be 0, right? So all of my other outputs, no matter what a is, seem to be bigger, right? So as a gets smaller, so this is 0, but as a gets small, right, you can see that my outputs get bigger. And then as we make a bigger and bigger and bigger, our outputs get smaller, but this is still our maximum. And then we never have anything that goes below 0. Right? Our outputs do get small, but they never go negative. So our global max for this family is always going to be at 1 over a, and then our global min will always be at 0. Okay, so two sides of the coin here, right? So if you're just looking at functions that have defined values and they have nice windows that you can look at them on, Desmos is a great tool, right, to understand the behavior. But for families, like taking one additional step and figuring out what those critical values are, depending on your parameters, can give you that additional insight to find those maximums of the families or minimums of the families. Okay. All right, so we're 2 minutes over. Just a brief wrap up here. So we're going to wrap up global optimization on Monday. We'll do maybe a couple of these examples together. And then the rest of the semester, we're going to be focused on this section, applied optimization, where you can think about them as word problems, right? So you're going to be given some sort of scenario, and we're going to have to optimize that. So an example of such a thing would be like this, right? So you're given a scenario is being described to you, and then you have to answer the questions where what would be the maximum area or minimum cost or something like that. All right. Okay, so let's call it here. Have a great weekend, everybody. I guess I didn't give you all a chance to ask questions, but you all have any questions about this before I sign off? All right, well, as usual, if you do have questions, if things come up, send me an email. I'm happy to answer them that way. But think about that homework for the weekend. You should be in good shape. And then we'll have some more applied optimization problems to do next week. Thanks for showing up. Have a great weekend.